We spend so much time focused on the obvious cyber defenses, firewalls, antivirus, the things we can kind of see. But what about the hidden infrastructure that, makes the modern web actually work? I'm talking about APIs, application programming interfaces. And here's a pretty shocking stat. Over 80% of all web traffic is powered by these things, 80%. Yet they often fly under the radar when we think about security. And here's where it gets really interesting. These APIs are basically the digital doorways allowing different applications to talk to each other. And because they're, well, designed to expose data, they can be a surprisingly direct route for attackers to get their hands on sensitive information, sometimes bypassing traditional security layers completely. Gartner even predicted, I think back then, that APIs would become the leading attack vector by 2022.
Yeah, what's fascinating there is how that prediction really highlights a major shift,
Yeah.
in the cybersecurity landscape. Attackers are increasingly targeting the connections between applications, recognizing the wealth of data and functionality they expose,
Yeah.
rather than solely focusing on, say, user-facing websites. And like you said, the sheer volume of API traffic just creates this huge target-rich environment.
Exactly. So, our mission for this deep dive is to really understand the world of API hacking. And we're diving deep into Corey Ball's excellent book, Hacking APIs: Breaking Web Application Programming Interfaces. It came out from No Starch Press in 2022. And for those who like the details, the print ISBN is 978-171-850-2444. Ebook is 978-171-850-2451. Cataloged under Application Program Interfaces and Application Software Development.
Right, and it's probably worth remembering, as Corey himself points out in the book, the information is provided as is.
Hmm.
The cybersecurity world moves incredibly fast, so, while the book is a fantastic foundation, it's really the snapshot of the knowledge of the time.
Right. Good point. And yet, sometimes the personal touches in books are kind of memorable. Corey dedicates it to his wife and daughters with this funny line about their distractions potentially costing the world a data breach or two. It's a good reminder that there's, well, a human element behind all this tech stuff.
It certainly brings it down to earth a bit, doesn't it?
Yeah.
Ultimately, the security of these complex digital systems relies on the expertise and vigilance of individuals.
Okay, so let's unpack this. In this deep dive, we're going to follow the structure of Corey's book to build our understanding, sort of step by step. We'll start with the basics of how web applications function, because APIs are built on the same technologies. Makes sense. Then we'll look at the specific anatomy of APIs, what they are, how they're put together. From there, we'll get into attack methods, explore some real-world examples of how these vulnerabilities get exploited, and finally, point you to some resources for further learning. Ready to get started?
Absolutely. Let's lay that foundation.
Okay, chapter 1 of Corey's book, it focuses on how web applications work. And the fundamental idea here is that to understand how to hack APIs, you first need to grasp the core concepts, right? The things that underpin all web interactions. APIs aren't some separate magic. They're built using the same basic web tech.
That's a really crucial insight, yeah. You can't effectively target APIs without understanding the underlying HTTP protocol, how authentication and authorization work in web environments, and, the fundamentals of the databases that often store and manage the data these applications use.
Exactly. So let's start with HTTP, the Hypertext Transfer Protocol. Corey breaks down the fundamental aspects, starting with the structure of a URL, that web address you type into your browser. He uses the example of a Twitter search URL, https://twitter.com/search.keycacking an SRC type free query. Can you give us a quick breakdown of what each part of that URL actually does?
Sure. So HTTPS tells your browser to use a secure connection.
Hmm.
HTTPS Twitter.com is obviously the website's address, the host name. Search points to the specific search function on Twitter servers. That's the path. And then anything after the question mark are parameters. Here, quacking is the search term, the query. And Gauss type query is likely telling Twitter, where the search came from. Basically, it's the web address, the specific page or resource you want, and then parameters giving more detail. When you use the Twitter website, your browser just assembles this URL based on what you click and type.
Okay, that makes sense. And once the browser has this URL, it sends an HTTP request to the server. What are the key types of HTTP requests we should know about? The methods.
Yeah, the main ones are get, post, put, head, and delete. Get is used to retrieve data, like when you load a web page. Pretty simple. Post is for sending data to the server, like submitting a form or, say, your login details. PutE is generally for storing or updating data at a specific location on the server. Head is kind of like get, but it only asks for the server's information about the data, the headers, not the data itself. And delete, well, as you'd expect, is for removing data. The key insight for attackers here, as Corey mentions, is that sometimes PuTTY and POD-A's can be used interchangeably in poorly designed APIs, potentially allowing some unintended data manipulation.
Ah, okay. So when you log into Twitter, for instance, the browser sends a post request. What does that look like behind the scenes?
Right. A PUIS request has headers, which are like metadata about the request, things like the content type authorization. And it also has a body, which contains the actual data being sent. For Twitter login, the body would typically have your username and password, maybe other details. Corey mentions that special characters in the body often get encoded so they don't, mess up the transmission, like an exclamation mark might become for 21 URL encoding.
Got it. Encoded. And after the server processes the request, it sends back an HTTP response. What are the important parts of that?
An HTTP response also has headers, and usually a body, which contains the requested data like a web page or JSON data. But a really crucial part is the status code. It's a 3-digit number that tells you if the request worked or not. Corey highlights 200 OK, which means everything worked perfectly. And 404 not found, meaning the resource you asked for just doesn't exist. These codes are vital clues for understanding how an API is behaving, both for legitimate use and, well, for figuring out potential weaknesses.
Beyond just getting data and sending it, web apps need to manage who can access what. That brings us to authentication and authorization. What's the core difference there?
Yeah, good distinction. Authentication is basically about proving who you are, like showing your ID with the username and password. It's the "are you who you say you are" part. Authorization is about what you're allowed to do after you've proven your identity. What permissions do you have?
Yep.
Just because you're logged in doesn't mean you can access everything. Your permissions determine that.
And modern web applications are often stateless. What does that actually mean, and why is it a good thing for scalability?
Stateless means the server doesn't remember anything about your previous interactions from one request to the next. Think of like a waiter who forgets everything about you after each interaction. You have to remind them of your entire order every single time. Stateless APIs work similarly. Each request has to contain all the info the server needs to process it, including authentication. In a shopping cart example, instead of the server constantly tracking your cart in memory, your browser might hold a token. That token identifies your cart contents, which are actually stored in a database on the server side. This allows the application to handle many, many more users because the server isn't tied up maintaining individual, continuous connections for everyone.
That makes a lot of sense for handling lots of users.
Yeah.
Okay. Finally, Chapter 1 touches on the databases that often power these web applications. What are some common types?
Corey introduces a couple of main categories. There are NoSQL databases like MongoDB, which are pretty flexible and good for handling different kinds of data structures, often seen with modern apps. And then there are the traditional SQL databases, which use a more structured table-based approach, relational databases. He gives a basic MongoDB query example, the db.collection.find, user ID 111, just showing how you look for a user with a specific ID. And he mentions operators like EQ for equals and do-free for greater than, which allow for more refined searches within NoSQL.
Okay, so a good grasp of HTTP, auth, statelessness, basic databases, that's our foundation. Solid. Now let's dive into Chapter 2 and the technical anatomy of APIs. What do we learn about the specifics of APIs themselves?
All right, Chapter 2 gets into what makes APIs tick. A key point is that API users or consumers interact with specific endpoints and resources. These are all defined in the API's documentation. Think of it like the API's instruction manual or contract. Corey really emphasizes that this documentation is crucial for both legitimate use and for anyone looking for vulnerabilities. It lays out the authentication requirements, different permission levels, the available endpoints, the parameters you need to send, and it can even give hints about the underlying business logic. The crucial insight, maybe the scary insight for defenders, is that this documentation essentially provides a map of the API, potentially making discovery much easier for an attacker.
So the documentation can unintentionally be a roadmap for how to attack it.
Pretty much, yeah. It reveals the intended structure and expected behavior, which an attacker can then probe for weaknesses, inconsistencies, or deviations from that expected behavior. Corey's an example from GitHub's API docs for an endpoint managing scope tokens. It clearly lists the parameters needed, client access token, their data types, string, where they go, path or body, and whether they're required. This level of detail is invaluable for understanding how to interact with the API, but also for spotting potential areas for manipulation or attack.
The book also mentions CRUD operations. What are those, and how do they typically map to HTTP methods in APIs?
CRUD stands for Create, Read, Update, and Delete. They're the fundamental actions you usually perform on data. In APIs, these often correspond pretty directly to HTTP methods. Create usually maps to post. Read typically maps to get. Update often uses poop, but sometimes post is used too. And delete generally maps to delete, although again, sometimes post is used. Corey notes that while this is a common practice or best practice, API developers might implement things differently. So it's important not to rely solely on these conventions when you're testing an API. You need to verify.
Now, the chapter introduces two main types of APIs we'll focus on: RESTful APIs and GraphQL. Let's start with RESTful APIs. What are their defining characteristics?
Okay, REST, or Representational State Transfer, it's an architectural style for building networked applications, primarily using HTTP. RESTful APIs were designed to be simpler and more efficient than older styles like OSOAP. Corey explains that REST has 6 main guiding principles or constraints: client-server architecture, statelessness, which we've discussed, cacheability, responses can be stored to improve performance, a uniform interface, a layered system, meaning you can have intermediaries like proxies, and code on demand, which is optional where the server can send executable code.
That uniform interface one sounds important, but maybe a bit abstract. Can you break that down in simpler terms?
Yeah, think of it like this. All interactions with the API should follow the same general set of rules, making it predictable. This includes how resources are identified. Each thing should have a unique address or URI, how you manipulate resources, usually through standard methods like get, post, put, delete on representations like JSON, making sure messages are self-descriptive, like using standard media types, and this idea of Hades hypermedia as the engine of application state, which basically means responses should ideally include links to guide the client on what actions they can take next. However, the key takeaway here isn't just the definition, but that REST is a flexible style, not a strict protocol. This means different APIs labeled RESTful can vary quite a bit in how they actually implement these principles, which is something attackers can definitely look for and potentially exploit. Variations are common.
Okay, so it's more a set of guiding principles. Got it. What are some common headers you'll typically encounter in REST API requests and responses?
Corey details several key ones. Authorization is obviously crucial. It's used to send your credentials or tokens, often in the format like bearer token or basic encoded credentials. Content type tells the server in a request or the client in a response what kind of data is in the message body. Application JSON is super common for REST. He also mentions X headers, which are often custom headers used by middleware or the specific API. Examples include XAPI key for API key authentication, and headers like XRate limit and XRate limit remaining. These rate limit headers tell you how many API calls you have left within a certain period. These custom headers can sometimes leak useful information to attackers too.
And speaking of data formats, the book highlights JSON. Why is JSON so popular with REST APIs?
JSON, JavaScript Object Notation, is just a really lightweight and easy-to-read way to format data. Humans can read it easily, machines can parse it easily. Corey explains it's all about key-value pairs inside curly brackets, separated by commas. Keys are always text strings in quotes, and values can be strings, numbers, booleans, true-false, null, arrays, which are lists in square brackets, or even other nested JSON objects. He gives a clear example in the book. While JSON is definitely king in the REST world today, he also briefly mentions XML, Extensible Markup Language, as another format. XML is more commonly associated with older SOAP APIs, but you can still see it used in some REST APIs.
Now, a critical aspect of any API interaction is authentication. Chapter 2 covers different methods. Let's start with stateful versus stateless authentication again, but specifically in the context of APIs.
Right. As we touched on, stateful authentication, often using server-side sessions and browser cookies, means the server remembers your session between requests. You log in once, get a cookie, and the server knows who you are based on that cookie. REST and GraphQL APIs, however, are generally designed to be stateless. This means each request you make has to contain all the information the server needs to verify who you are, usually in the form of a token or API key sent in a header.
What about basic authentication? We hear that term quite a bit, often not in a good way.
Yeah, basic authentication is a very simple method where you send your username and password with every single request. It's often encoded in base64, which Corey shows how to encode and decode easily using command line tools. But the crucial insight here isn't just how it works, but how fundamentally insecure it is. base64 is not encryption, it's just encoding, easily reversed. Anyone sniffing the traffic can grab the credentials, so you should almost never see it used over unencrypted HTTP, and even over HTTPS it's vulnerable to other attacks. Because of this, it's usually only used for maybe an initial setup step, after which the API typically issues a more secure token or key.
API keys seem like a slightly better approach then. How do those work?
API keys are basically like secret codes or passwords that identify your application or you to the API. Corey gives examples of them being passed in the URL as a query parameter in a specific custom header, like XAPI key or just API key, or sometimes even in a cookie. He uses the NASA API as an example where you'd register to get a key. When these keys are long, random, and complex, they are definitely much harder to guess or brute force than simple username password credentials used in basic auth.
Then there are JSON Web Tokens, or JWTs, pronounced JOTs. These seem to be everywhere now. What's their basic structure and what are some security concerns with them?
Okay, a JWT is a compact, URL-safe way to securely transmit information between parties as a JSON object. Corey explains it has three parts, separated by dots. A header, saying what kind of token it is and assigning algorithm used. A payload, containing the actual claims or data, like user ID, roles, expiration time. And a signature. All parts except the signature are base64 URL encoded. The signature is created using the header, the payload, a secret key for symmetric algorithms like HMAC, or a private key for asymmetric ones like RSA, and the algorithm specified in the header. This signature verifies that the token hasn't been tampered with. A potential security issue, though, is that while the signature ensures integrity, the header and payload are just base64 encoded, not encrypted by default, so their contents are easily readable by anyone who intercepts the token. Also, if the secret key used to create the signature is weak or gets compromised, attackers might be able to forge their own valid tokens. We'll get into attacking those later.
HMAC is another authentication method mentioned, often used by services like AWS. How does that work?
HMAC, or Hash-Based Message Authentication Code, it involves a secret key that both the API provider and the consumer know beforehand. When you make a request, you use this shared secret key to create a unique cryptographic hash of parts of the request data, like the method, path, timestamp, body. You then include this calculated hash, the HMAC, in your request, often in the authorization header. The server performs the exact same calculation using the secret key it knows. If the hash it calculates matches the one you sent, it proves two things: that you know the secret key and that the request data hasn't been altered in transit.
Finally, Chapter 2 touches on OAuth. We often see those sign in with Google or sign in with Facebook buttons. Is OAuth an authentication method itself?
That's a really common misunderstanding. Corey clarifies that OAuth versions 1.0a and 2.0 is actually primarily an authorization framework, not an authentication protocol itself. Though OAuth 2.0 is often used in authentication flows, like with OpenID Connect built on top of it, its main purpose is to allow a third-party application, like say a photo editing app, to access certain limited parts of your account on another service, like your Google Photos, without that third-party app needing your actual Google password. It's all about granting delegated permissions. You authorize the photo app to access your photos, but not your email, for example. Poorly implemented OAuth flows can introduce risks, though. Things like if the authorization codes can be intercepted, if redirect URLs aren't properly validated leading to phishing, or if tokens are leaked.
Okay. And to tie all this together, the chapter ends with an example of a Twitter API POST request. What does that illustrate?
Right, the example, POST 1.1 jot client event.json.hacking HTTP 1.1 shows a real API call in action. You see the HTTP method, POST, the specific API endpoint path, a parameter in the URL, the HTTP version, and importantly, it would typically include headers like host, content type, and an authorization header, perhaps with a bearer token like we discussed. This just brings together all the elements we've talked about, how requests are structured, and how authentication information is typically included.
So chapters 1 and 2 have given us a really solid foundation in web application basics and the technical details of APIs. We've covered everything from HTTP methods to various authentication approaches. Now we're jumping ahead a bit in the book. Chapters 3, 4, and 5 cover setting up a lab environment, essential tools like Burp Suite, Kitterunner, OWASP Amass, and Postman in more detail. Crucial for hands-on practice, definitely. But for this deep dive, we want to move on to Chapter 6, which is all about discovery, because, well, before you can even think about hacking an API, you need to find it, right?
Absolutely. Chapter 6 is all about reconnaissance information gathering. Corey emphasizes that the very first step in any API security testing engagement is finding the APIs a target actually uses and verifying that they're live and functioning. You simply can't attack what you can't find.
He even mentions that sometimes during this initial OSINT open source intelligence collection phase, you might just stumble upon some really obvious high-risk security issues right away, like exposed API keys or credentials. What should you do if you find something like that?
Yeah, Corey rightly points out that discovering exposed sensitive information like API keys, passwords, JWTs, or even PII, personally identifiable information, is a critical finding. This kind of information should be immediately and responsibly reported to the organization because it represents a direct and significant security risk that needs urgent attention. Don't try to exploit it further, just report it.
Good advice. The chapter then dives into the passive recon process. What does that involve? How do you gather info without tipping off the target?
Passive reconnaissance is all about gathering information about your target without directly interacting with their system, so they likely won't detect your activities. The goal is to build a picture of their online presence, their technology stack, and understand how they might be using APIs, which can vary a lot by industry. Corey describes it in two phases. Phase 1 is casting a wide net, using publicly available information sources, things like search engines, Google, Bing, DuckDuckGo. Looking at job postings, they often mention specific technologies or APIs used, checking social media profiles, company or employee, reading security blogs or news for mentions. He also mentions using tools like DNS Dumpster to visualize their DNS records, and as we mentioned, OWASP Amass to get an overview of their known internet-facing assets or attack surface.
And phase 2 of passive recon is about narrowing that focus based on what you've already learned.
Exactly. Based on the initial information gathered in phase 1, you start to refine your search. This might involve using more specific search terms, combining insights from different sources, looking for related code repositories on places like GitHub. Developers sometimes accidentally commit keys or sensitive info. And using tools like Paste Hunter or similar services to check public paste sites, like Pastemin, for any sensitive information related to the target that might have been accidentally leaked.
The book then gives some examples of Google Dorks, those specialized search queries that can uncover surprisingly specific information. Can you give us a couple of the API-related examples he provides?
Sure, Corey provides several good ones. One is entitle.index.of-intex.api.txt, which tries to find publicly accessible directory listings that contain a file named api.txt, which might hold keys. Another is enurl.include-sapientext.index, of looking for exposed directories potentially related to APIs. His favorite query, as he calls it, is entitled index of APR or APKey or APKey pool. This looks for directory listings containing files or text with variations of APKey, and as figure 6:1 in the book illustrates, this can uncover a surprisingly large number of potentially exposed keys.
That's a bit concerning how easily that stuff can be found sometimes. Are there other specific online resources that are good for finding information about APIs themselves, like directories?
Yes, definitely. Corey highlights Programmable Web as a key resource. It's a huge directory listing thousands of public APIs, often with details about them, plus articles and learning resources in its API University. You can often find details about API endpoints, versions, how they work, business logic, their status, code examples, SDKs, links to documentation, changelogs, tutorials, and even news related to specific APIs. He also mentions other API directories like Rapid API, which also includes marketplaces, and apis.guru, which focuses on API specifications.
What about Shodan? We often hear that mentioned in the context of finding exposed devices. How can it be helpful for API discovery?
Shodan is basically a search engine for internet-connected devices, not just websites. It constantly scans the internet and catalogs information about open ports, running services, banners, and device types. This can be useful for finding externally facing APIs by searching for specific IP address ranges belonging to the target organization, or searching by organization name. You'd look for services running on common web ports like 8443, 8080, 8443, or look for specific server headers or response bodies that might indicate an API is present, like seeing content type application JSON.
And we've mentioned OWASP Amass a couple of times. How does that fit specifically into the passive reconnaissance picture for APIs?
Right, OWASP Amass is a really powerful command line tool specifically for network mapping and attack surface discovery. It gathers OSINT from dozens of different sources, search engines, certificate transparency logs, DNS records, web archives, search APIs, etc. You can run it in passive mode to discover subdomains and other related internet assets belonging to your target without sending any traffic directly to the target systems. Corey gives examples of using the Amass Intel subcommand to gather SSL certificates associated with a domain, which can reveal subdomains, and perform reverse whos lookups to find more domains owned by the same entity.
Okay, so that's a pretty thorough look at passive reconnaissance gathering info without touching the target. What about the active recon process? How does that differ?
Active reconnaissance involves directly interacting with the target systems to gather more detailed information. It's generally noisier and more likely to be detected. Corey outlines a three-phase approach for this. Phase 1 is detection scanning, typically using tools like Nmap for port scanning to find running HTTP or HTTPS services on the target's infrastructure. Phase 2 is hands-on analysis. This is where you manually explore the web applications and any identified API clients, like mobile apps, from different user perspectives. Guest, authenticated user, maybe admin if possible. The goal is to understand how they function, map out the business logic, and look specifically for API interaction points. This includes examining web pages' source code, intercepting network traffic with a proxy like Burp Suite or ZAP, and actively looking for links to API documentation or developer portals. Phase 3 is targeted scanning. Based on what you discovered in Phase 2, you focus your automated scans, like deeper Nmap scans or vulnerability scans, on the specific ports and services you identified as potentially interesting. It's kind of an iterative process: explore, scan, analyze, explore more.
What are some of the key tools used during this active reconnaissance phase?
Corey highlights browser developer tools, like in Chrome, Firefox, Edge, as absolutely essential for the manual analysis part. He briefly explains the purpose of the console for errors and logging, sources to inspect code, network, crucial for seeing all requests, including API calls, performance for timing, and application for storage like cookies, local storage. The network tab is gold here. He also reintroduces ZIP, OSP, Z attack proxy, specifically mentioning its heads-up display, HUD, which overlays controls and information directly onto your browser, allowing for real-time vulnerability scanning as you browse the target application. For quickly finding potential directories and files, including API paths, he mentions GoBuster, a common tool for brute-forcing URLs. But he specifically recommends KitterRunner, which he covers in Chapter 4, as a particularly effective tool for discovering API endpoints and resources. KitterRunner is designed to try various HTTP methods, not just GET, and mimic common API path structures, making it potentially better suited for API discovery than a general directory brute forcer like GoBuster.
And to illustrate active reconnaissance, the book provides an example Nmap scan. What did that particular scan show?
Right, the example Nmap scanned against a specific IP address from the Cree API vulnerable application reveals several open ports, including some commonly used for web services like 8000, 8080, 8888. Importantly, it also attempts to identify the services and versions running on those ports. Corey points out a specific response from port 8080 that returned a content type application JSON header and an error message like error, invalid token. This combination strongly indicates the presence of an API running on that port that likely requires authentication via token.
Finally, Chapter 6 discusses common places to look for that elusive API documentation. Where should you typically search if it's not immediately obvious?
Corey lists several common URL patterns developers often use for documentation. Things like just docs or apadocs appended to the main domain. Also look for specific subdomains like docs.target.com, dev.target.com, developer.target.com, or api.target.com, often followed by docs. He suggests that if you can't find public documentation, it's definitely worth creating an account on the target application and looking for developer sections or documentation links after you've logged in. Sometimes docs are only available to registered users. He even mentions using word lists, like those found on GitHub. He links to his own Hacking APIs repository, containing common subdomain names and directory paths used for APIs and documentation, which can be fed into tools like GoBuster or FUF for brute-forcing discovery.
Okay, so Chapter 6 gives us a really comprehensive toolkit and methodology for finding APIs, both passively and actively. Once we've located those endpoints, what's the next logical step? That takes us to Chapter 7, API Endpoint Analysis, getting into the details.
Exactly. Chapter 7 focuses on taking those discovered API endpoints and diving deeper. The goal here is to understand exactly what each endpoint does, what data it expects, what data it returns, and identify any potential weaknesses before we start actively trying to exploit them. It's about building that detailed understanding.
And the book introduces Postman as a key tool for this analysis stage. Why is Postman so valuable here?
Postman is described as a very popular API development and testing platform. It's fantastic for manually crafting HTTP requests, sending them to API endpoints, and then visualizing and analyzing the responses you get back. It supports various API types like REST, SOAP, and GraphQL, and it offers a bunch of useful features. An intuitive request builder, the ability to organize requests into collections, which is great for complex APIs, scripting capabilities for adding dynamic behavior or tests, automated testing features, and even documentation management. Corey provides instructions for setting it up, for instance, on Kali Linux, a popular pen testing distribution.
The chapter then describes the Postman Request Builder interface. What are some of its key components for constructing and sending these API calls?
Right. The Postman Request Builder, as shown in Figure 415 of the book, has several important tabs that you'll use constantly. The Params tab is for adding query parameters to your URL easily, the stuff after the clam. The Headers tab allows you to define custom HTTP headers, which are often essential for things like authorization tokens, content type specification, or custom API keys, XAPI key, etc. And the Body tab is where you construct the request payload, often in formats like JSON, XML, form data, or XWWA form Erlang coded, depending on what the API expects. Corey highlights the use of variables in Postman, like setting a base URL or an auth token as a variable. This is really helpful for managing dynamic parts of requests efficiently. He also introduces the concept of Postman collections for organizing related API requests and environments for managing different sets of variables, like having separate variables for development, staging, and production APIs.
One of the really useful features of Postman seems to be the ability to import API specifications like OpenAPI or Swagger files. How does that speed up the analysis process?
Yeah, that's a huge time saver. If an API provider makes a formal specification document available, like an OpenAPI JSON or YAML file, you can import it directly into Postman. Postman will then automatically parse this file and create a ready-to-use collection with all the defined endpoints, their associated HTTP methods, expected parameters, required headers, and sometimes even example requests. As Figure 7-5 shows in the context of collection variables, this can save a massive amount of tedious manual effort compared to creating each request from scratch just by looking at documentation.
But what if you find an API and there's absolutely no documentation or specification file available? How do you even begin to understand what it does in that case, the black box scenario?
Right, in those cases, you have to engage in reverse engineering the API. Corey explains that this involves interacting with the client application, web or mobile, that uses the API, intercepting the traffic between the client and the API using a proxy like Burp Suite or Postman's built-in proxy, and then carefully observing the requests being made and the responses being received to gradually piece together the API's functionality, endpoints, parameters, and authentication mechanisms. He notes that for APIs with many endpoints, this can get complex quickly, which is why using Postman collections to organize your findings as you discover them is crucial. He describes a couple of ways to build these collections without a spec, manually adding requests in Postman as you identify them through proxying, and configuring Postman itself to act as a proxy to directly capture the API calls your web browser or mobile app makes. He also recommends proxying the output from discovery tools like KitterRunner through Burp Suite, another powerful security testing tool, so you can easily capture those discovered endpoints and replay or analyze interesting requests within Burp or send them to Postman.
Okay, so once you've captured these API requests, either from a spec or through reverse engineering, what should you focus on when analyzing both the requests and the responses?
The initial focus, Corey emphasizes, should be on understanding the normal expected behavior of the API for valid requests. You need a baseline. What does a successful request look like? What does a valid response contain? This gives you a foundation before you start trying to find vulnerabilities by sending invalid or malicious requests. He illustrates this with a GET request to Pixie's Epiduos Info endpoint in Postman, noting that it requires an X-access token header containing a JWT. A successful 200 OK response shows the API is working correctly and returns expected user info. He also shows the requirements for an administrative endpoint in Pixie, emphasizing that identifying these protected areas is a key step towards the goal of trying to gain higher privileges later on. More generally, he stresses the importance of analyzing the HTTP status codes, 200, 401, 403, 404, 500, etc., all the headers, especially content type, authorization, custom X headers, and critically, the content of the response body, often JSON, for any clues about the API's functionality, data structures, and potential weaknesses like information disclosure.
The chapter also touches on transit insecurities. What are those, and why are they a security risk specifically for APIs?
Transit insecurities refer to the risks of data being exposed while it's traveling over the network between the API client and the API server. Corey points out the obvious risk. If an API uses plain HTTP without the S for secure, the traffic is unencrypted. Anyone on the same network path, like on public Wi-Fi, can potentially intercept and read the data using tools like Wireshark. This includes sensitive things like passwords or API tokens and in requests. Even if the API provider enforces HTTPS on their server, there's a risk if a client application initiates a request over HTTP first. Any sensitive information in that initial HTTP request, like authentication tokens in the URL or headers, could be exposed in plain text before the connection potentially gets redirected to HTTPS by the server. Figure 714 shows an example of a token being sent over HTTP.
And to really highlight the importance of analyzing those API responses carefully, the chapter uses an example from the deliberately vulnerable application, Koryak API, completely ridiculous API.
What did that example reveal about data exposure?
Right. Corey describes intercepting a request made when a user submits a comment in the Create API forum, a post request. He then shows sending a related GET request to the Community API2 Community Post Recent endpoint to fetch recent forum posts. The JSON response body, returned by this GET request, shown in Listing 7.1, contained a surprisingly large amount of information, not just about the posts themselves, but also detailed information about other users. This included their internal IDs, the full content of their posts, author details like nicknames, email addresses, vehicle IDs, profile picture URLs, and even the exact timestamps of when their posts were created. This is a prime example of what's called excessive data exposure, a very common API vulnerability. The API is returning far more information than the client application actually needs or displays, potentially revealing sensitive data about other users to anyone who inspects the API traffic.
Wow, yeah, leaking emails and vehicle IDs is definitely excessive. Okay, so Chapter 7 equips us with the tools and techniques to really dissect API endpoints and understand their inner workings, which perfectly sets the stage for the next phase, actually attacking them. And that brings us to Chapter 8, which focuses squarely on attacking authentication.
Exactly. Chapter 8 shifts our focus from analysis to actively targeting the mechanisms that control who can access the API and its resources. Corey explains that the goal of these authentication attacks is generally threefold. Bypass authentication entirely to gain access without credentials, gain access to resources belonging to other users, or elevate privileges from a standard user to gain administrative or higher level control.
The chapter starts by covering classic authentication attacks. What are some of the traditional methods that attackers still try and which can still be effective against APIs?
Corey revisits basic authentication, which we discussed earlier, reminding us of its inherent weaknesses and why it's generally a bad idea. Easy interception. He then moves on to brute force attacks. This is the straightforward approach of trying many different username and password combinations until you find a valid one. He notes that the response the API gives after a failed login attempt can provide valuable clues. A generic, incorrect username or password is less helpful to an attacker than a response that specifically indicates username not found or incorrect password, as the latter confirms the username exists, aiding in targeted attacks. He also covers password spraying. Instead of trying many passwords for one user, you try a small list of very common passwords, like password 123 spring 2024, against a large list of potential usernames. This is often more effective against systems with account lockout policies, as it avoids locking out individual accounts quickly. Usernames can often be gathered from reconnaissance or other data exposure vulnerabilities.
And the book details how to set up these brute force and password spraying attacks using a common tool, Burp Suite Intruder. What are some of the key configurations involved in setting that up?
Corey explains using Burp Suite Intruder's cluster bomb attack type. This is useful for testing multiple positions with different payload lists, simultaneously perfect for login forms where you need to vary both the username and the password. You first intercept a valid login request in Burp Proxy, then you send it to Intruder and define attack positions, using these symbols, around the username and password fields in the request. Figure 8.2 illustrates targeting usernames within a specific email domain. You then configure two payload sets, one with your list of potential usernames and another with your list of passwords, as shown in Figure 8.3. Intruder will then systematically try every combination. He also mentions a crucial tip. After the attack runs, sorting the Intruder results table by status code or response length can help you quickly spot any anomalies responses that differ from the standard login failed response, which might indicate a successful login.
Sometimes APIs might try to obscure authentication credentials by encoding them, maybe using base64. Does that offer any real security against these attacks?
Not really, no. Corey is very clear that base64 encoding is not a security measure. It's simply a standard way to represent binary data in an ASCII string format and is trivially reversible. Anyone can decode it. If you encounter an API using base64 for authentication, perhaps with the authorization, basic header, or maybe even in a custom scheme, the book explains how to adapt your fuzzing or brute force attacks in Burp Suite Intruder to handle this. You can configure Intruder's payload processing rules to automatically base64 encode your username password payloads before sending them, or even automatically decode parts of the API's responses to better understand how it's working. Figures 8.5 and 8.6 show how to set up payload processing rules for encoding and decoding.
Okay, so basic creds are one thing. The chapter then moves on to attacks targeting tokens, including forging tokens. How might an attacker attempt to create or manipulate authentication tokens?
Corey explains that while tokens like API keys or JWTs are generally a more secure way to handle authentication in stateless APIs compared to sending passwords repeatedly, they can become a vulnerability if the way they are generated is predictable, if they contain sensitive information that's not properly protected, or if they are accidentally leaked or stolen, as we discussed in Discovery. The key to forging or hijacking tokens often lies in analyzing the structure and patterns within the tokens issued by the API. Are parts of the token sequential? Do they contain easily guessable information like user IDs or timestamps? Is the entropy randomness low? If you can identify any non-random or predictable elements, you might be able to generate your own valid-looking tokens or manipulate parts of existing ones. He suggests using Burp Suite Intruder or another fuzzer like Wufuzz to try brute forcing parts of tokens that appear less random or might be guessable, as illustrated in figures 8.11 and 8.12, setting payload positions on specific parts of the token value.
And of course, given their prevalence, we have to talk specifically about JWT attacks. What are some common vulnerabilities associated with JSON web tokens?
Corey details several common JWT attack vectors. One well-known one is the none algorithm attack. This exploits JWT libraries or implementations that incorrectly trust the OWL algorithm header field within the JWT itself. An attacker modifies the header to specify alg, none, and removes the signature part. If the server blindly trusts the header and sees none, it might skip the signature verification altogether, accepting the potentially modified payload. He mentions the JW tool is useful for automating this, shown in figure 8.13. Another is the algorithm confusion or key confusion attack. This typically applies when an API uses asymmetric keys, RSA, ECDSA, for finding, but also accepts symmetric keys, XMAC. An attacker takes the public key, modifies the JWT header to claim it's using an HMAC algorithm like HS256, and then signs the token using the public key as if it were the HMAC secret key. If the server doesn't properly validate that the algorithm matches the key type, it might verify the signature using the public key as the secret, allowing the attacker to forge tokens. Again, JW tool can help identify and exploit this. He also notes that even if strong algorithms are used, if the secret key used to sign the JWT for HMAC is weak or easily guessable, like secret 1 to 3, it might be susceptible to offline brute force attacks using tools like Hashcat.
Interesting attack vectors. The chapter concludes with a lab focused on cracking a CryPI JWT signature. What's the objective of that exercise, and what does it demonstrate?
Right, Lab 5 focuses on attacking the JWT that the CryPI application issues after a user is successfully authenticated. You're encouraged to capture a valid JWT and analyze its structure using an online debugger like jwt.io, as shown in figure 8.14. This lets you easily see the decoded header, which specifies the HS512 algorithm in CryPI's case, and the payload containing claims like the user's email, issuance time E8, and expiration time expert. The lab then suggests exploring the none algorithm attack as a potential first step, although it might not work if the server validates correctly. Since CryPI uses a symmetric key algorithm, HMAC HHA512, the algorithm confusion attack isn't directly applicable here either. Therefore, the focus shifts towards the possibility of actually cracking the JWT signature by brute forcing the underlying secret key. This highlights that even robust algorithms like HS512 aren't foolproof if the secret key itself is weak, predictable, or sourced from a common word list. The lab implies you might be able to crack it if the key is weak enough.
So Chapter 8 gives us a good toolkit for attacking the front door, essentially the API's authentication mechanisms. Now let's move on to Chapter 9, which delves into a really fundamental technique: fuzzing.
Yeah. Chapter 9 introduces fuzzing as a crucial, often automated technique for discovering API vulnerabilities. It's fundamentally about sending unexpected, malformed, or just a huge volume of varied data to the API and carefully observing how it reacts. You're looking for crashes, errors, unexpected successful responses, delays, or any other signs of underlying weaknesses or bugs.
The book makes a distinction between wide fuzzing and deep fuzzing. What's the difference in their scope and goals?
Corey explains that wide fuzzing is like casting a broad net. It involves testing across many different unique API requests or endpoints, often with a smaller, more targeted set of payloads for each. The goal is to uncover general issues across the API surface. This might include things like finding undocumented endpoints or parameters,
improper asset management, discovering which HTTP methods are accepted on various endpoints, how different authentication tokens are handled across the entire API, or finding instances of information disclosure and error messages. Think of it as broad exploratory probing. Deep fuzzing, on the other hand, focuses intensely on one or a few individual API requests or endpoints. It involves testing many different aspects within that single request, maybe specific URL parameters, headers, or fields within the request body, using a large and diverse set of fuzzing inputs or payloads. This is more targeted at finding specific vulnerability types within that endpoint, like broken object level authorization, BOLA, broken function level authorization, BFLA, various injection flaws, SECY, NoSQL, command injection, XSS, or mass assignment vulnerabilities. It's about depth over breadth.
Makes sense. So what are the essential components you need to set up a fuzzing attack, regardless of whether you're going wide or deep?
You need a few key things. First, your tools Corey primarily focuses on Burp Suite Intruder and the command line tool WayFuzz as the workhorses for API fuzzing. Second, you need to identify the payload positions within your base HTTP requests. These are the specific parts of the request, like a URL path segment, a query parameter value, a header value, or a field within a JSON body that you want the fuzzer to modify and inject payloads into. Third, you need your payloads themselves. These are the lists of values that the fuzzer will insert into the payload positions. These could be lists of common vulnerability strings, like SQL injection snippets, XSS vectors, special characters, edge case values, like large numbers, empty strings, nulls, or comprehensive lists, like the big list of naughty strings. You might create custom lists or use pre-existing ones like those in seek lists. And finally, you need to ensure you're using the correct HTTP method, get, he, post, put, delete, etc., for the specific API endpoint you're testing, as the API will likely only respond correctly to certain methods.
Can you give us an example of how you might use fuzzing wide in practice, based on the book?
Corey illustrates wide fuzzing with the example of testing different HTTP methods against various API endpoints to see which ones are supported, potentially uncovering endpoints that respond unexpectedly to methods they shouldn't. He shows setting up a PUT request in Postman, perhaps one discovered earlier, and then sending it to Burp Suite Intruder. He might select the HTTP method itself as a payload position, or maybe test a list of discovered endpoints against a list of methods. Using Intruder's sniper attack type, he could cycle through a payload list containing common HTTP methods, get, post, put, patch, delete, head, options, trace, connect, etc., against a target endpoint, as conceptually shown in Figure 9-6, focusing on field values. He also provides a WebFuzz command line example to achieve a similar outcome. WebFuzz list, get, head, post, put, patch, trace, options, connect, next, fuzz, http.testsite.com, /v2 account. Here, Mac OVZ list provides the payload list of methods, and Mac's FUZZ tells WebFuzz to use each item from the list as the HTTP method for the request.
And how does fuzzing deep differ in its execution and setup?
In deep fuzzing, you're much more strategic and focused about selecting your payload positions. Instead of testing everything broadly, you zero in on specific parameters or fields that seem interesting or potentially vulnerable based on your analysis. For example, if you're testing an endpoint that updates a user profile via a PUT request with a JSON body, you might focus your fuzzing payload specifically on the email field, or the user ID parameter in the URL, or maybe a specific security-related field. Corey gives a WeFuzz example demonstrating deep fuzzing of a request body. wfuzz dev file, patho payload wh content type application JSON, w for accounts and x, access token, wp127.0.1.808 is at http hd 400 and x pu1 bmd bvud pram1 dev2 best apttdd. Here, netivuzd keyword indicates the exact position within the JSON body where WeFuzz should inject each payload from the file. The HE400 option tells WeFuzz to hide responses with the 400 status code, helping focus on more interesting results.
Chapter 9 wraps up with a lab focused on fuzzing for improper assets management vulnerabilities in the Cree API application. What does that involve? And what's the outcome?
All right, Lab 6 guides you to use fuzzing techniques to find issues related to how CRAPI handles different versions of its API endpoints, which falls under the category of improper assets management, part of the OWASP API Security Top 10. You start by building or using a Postman collection for CRAPI with a valid authentication token from Chapter 7's work. Then you use Postman's environment variables and collection runner to fuzz wide for different API version paths. You might set a variable path initially to v3, as shown in Figure 9 and 10, finding replacing v2 with free. An interesting discovery is that while most CRAPI endpoints seem to use v2 in their path, the password reset OTP check endpoint uses identityAPIAuth v3 check a body. This inconsistency is a clue. When you run the collection with path set to v3, most requests fail with a 404 not found, as expected. However, the password reset endpoint returns a 500 internal server error instead an anomaly. Further investigation, maybe trying v2 on the password reset endpoint, reveals that the v3 version apparently has a rate limit on OTP attempts, giving a 500 error. However, the v2 version of the same logical function, though perhaps unintentionally exposed or deprecated, also gives a 500 error but seems to lack this rate limit. This discrepancy in older or alternative path for a function still being active but lacking the security controls of the current version is the improper assets management vulnerability. The lab then guides you to perform a deep fuzzing attack, brute force, on the v2 password reset endpoint, trying all possible 4-digit OTPs, 00000 to 9999. Since this v2 path lacks the rate limit, you can eventually guess the correct OTP and get a 200 OK response verifying it, potentially allowing account takeover.
That's a fantastic example of how fuzzing can uncover subtle but critical flaws, like inconsistent security controls across different API versions. Okay, so fuzzing is clearly powerful. Now we're moving on to Chapter 10, Exploiting Authorization. This seems like where the really impactful stuff happens, accessing things you definitely shouldn't be able to.
Exactly. Chapter 10 focuses on two extremely common and often high-impact authorization vulnerabilities in APIs. BOLO, which stands for Broken Object Level Authorization, and BFLA, Broken Function Level Authorization. Both are consistently in the OWASP API Security Top 10. BOLE happens when an authenticated user can access specific data objects, like another user's profile, order, or message, that they shouldn't have permission to access, usually by manipulating object IDs in the API request. BFLA occurs when a user can perform actions or access API functions that their assigned role or privilege level shouldn't allow them to, like a regular user accessing an admin-only endpoint.
BOLE in particular seems to be incredibly prevalent and can lead to massive data exposure. How do you typically look for BOLA vulnerabilities in APIs? What are the common patterns?
Corey explains that finding BOLEs often involves first identifying how the API refers to specific resources or objects, which is usually done through some kind of identifier ID in the URL path or in query parameters or the request body. For example, if you make a request to Pazers 123 orders 456 to get order details for your own user ID, 123, and a specific order ID, 456, the immediate test for BOLE is to try changing the user ID to someone else's, like APIOS 789 orders 456. If the API returns data for user 789's order, that's a BOLE flaw. He provides a table, Able 10-to-1, outlining common resource ID formats you might encounter. Simple sequential IDs like orders 1, orders 2, user-based IDs like users my profile versus user somebody else's profile, IDs for multiple objects, predictable tokens used as IDs, or combinations of IDs, like needing both a user ID and a resource ID, or a group ID and a resource ID. Understanding the ID patterns is key. He also suggests a simple but sometimes effective trick. If you find an API function where one HTTP method, like getD or PUT, seems properly restricted based on authorization, try using a different related method like post or maybe even patch or delete on the same resource URL. Sometimes developers implement authorization checks correctly for one method, but forget to apply them consistently to others, performing similar actions on the same resource.
For APIs with a huge number of endpoints, like in large applications, manually testing every single endpoint for these authorization issues with different user accounts sounds incredibly time-consuming. Are there any techniques or tool features that can help automate or speed up this process?
Yes, definitely. Testing authorization thoroughly across a large API surface can be tedious. Corey provides a couple of useful strategies to make it more efficient. One is to leverage Postman's collection variables and runner. You can capture all the API requests for your application into a Postman collection. Then, set the authorization token, like a JWT, as a collection variable. First, run the entire collection using your user's token, user A, and save the results. Then, obtain a token for a different user, user B, update the collection variable with user B's token, and run the collection again. By comparing the results, especially looking for requests that previously failed for user B but now succeed, or requests that return user A's private data even when using user B's token, you can quickly identify potential BLA or BFLA issues. Filtering collection runner results for anomalous status codes, like unexpected 200s, can highlight problems. The second tip is to use Burp Suite's match and replace rules in the proxy options, shown in Figure 10-2. You can configure Burp to automatically find user A's authentication token in all outgoing requests and replace it with user B's token. This allows you to simply browse the application as user A, but all the underlying API requests will be sent using user B's credentials. making it easy to spot pages or data you shouldn't have access to.
Those sound like really practical ways to scale up testing. Chapter 10 concludes with another Cray API lab, this time attempting to find another user's vehicle location. How is that BOLA vulnerability uncovered in the lab?
Right, Lab 7 focuses on identifying how CrayPI handles resource identifiers and testing for below. The lab notes that CrayPI doesn't use resource IDs and URLs very often, making BOLA perhaps less obvious initially. However, one request stands out. When the user clicks the refresh location button for their vehicle in the web interface, the browser makes a GET request to an endpoint like Identity IPv2 vehicle, 3 B4B8, 6DF6, 4134, AD32, 1B402, CAF45 location. That long string is clearly a unique identifier for the vehicle, likely a GI or UUID. The lab then guides you to perform a direct bull or attack attempt. Simply take that request, maybe capture it in Burp Postman, and manually change the vehicle ID GI to a different, potentially guessable or previously discovered key ID, as shown conceptually in listing 10-5. Surprisingly, when you send this modified request, CrayPI returns a 200 OK response, listing 10-6, containing the carry, the current vehicle location, latitude and longitude, and even the full name of the other user associated with that different vehicle ID. This is a clear and high-impact BOLA vulnerability. You can track other users' vehicles. The lab then cleverly connects this finding back to the excessive data exposure vulnerability we discussed from Chapter 7, found in the Community IPv2 community post-recent endpoint, listing 7-1. Remember how that endpoint leaked other users' details, including their vehicle and authority? This exposed information can now be directly used to make the BLA attack much more targeted and effective, because you can discover the actual vehicle GIs of other specific users from the forum post's leak. This demonstrates how vulnerabilities often chain together. A lower severity info leak enables a higher severity authorization bypass.
That's a fantastic practical example of chaining vulnerabilities. Finding the vehicle ID from one leaky endpoint lets you exploit the BOLA in another. Okay, serious stuff. Now let's move on to Chapter 11, Exploiting Injection Flaws. This sounds like it covers a whole range of ways to sneak malicious input past the API's defenses. What are some of the key injection types relevant to APIs discussed here?
Chapter 11 covers several important categories of injection flaws that can plague APIs. These include mass assignment, various forms of scripting injection like cross-site scripting, XSS, and the less common cross-API scripting, XAS, database-specific injections targeting both SQL and NoSQL databases, and finally, operating system OS command injection.
Mass assignment seems particularly insidious, especially for privilege escalation. What exactly is it, and how can it be exploited in an API context?
Mass assignment, sometimes called auto-binding, happens when an API endpoint allows a client to update internal object properties on the back end that they shouldn't actually have direct control over, often because the framework automatically maps incoming request parameters to back-end object fields. A classic scenario Corey describes is during user registration or profile update functions. An attacker might try to include an extra parameter in the JSON data they send, like IsAdmin true or role administrator. If the API backend code blindly takes all provided parameters and uses them to update the user object in the database without proper validation or filtering of allowed fields, it could inadvertently grant administrative privileges to a regular user, leading to complete account takeover or system compromise. He emphasizes that this isn't just limited to account creation. It can potentially occur in password reset functions, profile updates, order modifications, or basically anywhere user-provided data is used to update backend data objects based on parameter names.
Given that API parameter names for things like roles can vary so much, IsAdmin role, privilege, etc., how do you even begin to identify potential mass assignment vulnerabilities? It seems like guesswork.
Corey acknowledges that the inconsistency in parameter naming across different APIs makes finding mass assignment issues challenging. It's not always obvious what hidden parameter name might grant privileges, while fuzzing by trying various common parameter names, like admin, IsAdmin, role, debug, credits, balance, can sometimes uncover these. It's often more effective if you have some insight into the API's internal object structure or naming conventions. You might get clues by carefully analyzing the API's responses. Does it ever return an object with an IsAdmin field? Looking at API documentation, if available, it might hint at user object properties, examining the client-side JavaScript code that interacts with the API, or intercepting and analyzing all API requests and responses during normal application use to see what parameters are typically used.
The book then discusses using tools like Argin and Burp Suite Intruder to help automate the search for these potentially injectable parameters. How do those tools assist in this specific task?
Argin is a tool specifically designed for discovering hidden HTTP parameters. You could provide it with a known API endpoint URL and a sample request, including headers and maybe a sample body. Argent will then methodically try adding various potential parameter names from its built-in lists or custom lists to the request in the URL or sometimes the body to see if the server's response changes, indicating the parameter might be recognized. Cori provides an example command using Argent's headers option for tokens, data for a JSON body, and the Argent place